Now let's move on to step number 2 to calibrate. We are now going to create master calibration frames from the individual calibration frames. So you can leave everything in this step on automatic, as the correct statistics will be selected automatically. You can see there's also a bad pixel map. So what is that? The bad pixel map will also be created automatically, and it is very useful as it takes care of the defect pixels in the camera. Then there are a few more options lower down. There's one option I would like to make you aware of, that is to scale the master darks. This means that as long as your master dark exposure time exceeds that of your light frames, it can scale, assuming the camera behaves linearly. We don't need to do that here, so all we do now is click on Create Masters and Assign to Lights. This will take several minutes, so I'm just going to halt here and then continue. You'll be greeted with a loud gong to wake you up, because we can now continue. So let's expand the lower window. And as you can see, the labelings have changed on our light frames. Let's click on the first one and just take a look. You can see here it still says light blue session, and then it says MB1, which stands for master bias. Then comes the master darks. The master flats have been applied. The bad pixel map has been applied, and this means that was the complete calibration. Be sure to check all your images and make sure that this has all been applied correctly. Below that are the flats and the darks and the bias, and right on the lower end there are new files that have been created that are now stored in your work directory. That is the bad pixel map, the master flats, the darks, master darks, and also the master bias. These are quite useful because you can apply them in future when you have to do the calibration again, and you do not have to create them again. So let's take a closer look and to see what the quality is like. Let's load the first image. I'm just going to double click on it. And here we can use the image viewer very effectively. As you can see, the image looks a little bit dim. On the right hand side you can see the histogram, so let's stretch it a bit. Here is the stretch window. If you go all the way down, which is very useful, so we go from 15% 3 sigma 2.5% base all the way down to the 30% 2 sigma, and now you can see this was the raw image. It's still on linear, so this is the raw uncalibrated image. So let's zoom in, and you can see there's still some defects here. And also let's zoom in further, and you can see there are certain hot pixels here. You see those white little spots? Those are hot pixels, and there are also some cold pixels and so on. So you can now dynamically work through your workflow in the first step. So let's click on Calibrated, because we've done that already, and see how the image changes. And you can see all the hot pixels have disappeared. The line is still there. So what has happened here? The bad pixel map that we created has really worked very effectively, and it is very useful to examine your images that way. Now there's still a black line, which we call a cold column here, which the bad pixel map hasn't eliminated. And this is the important step, the next one we're going to do now. We're going to look at the cosmetic correction. We scroll down to the cosmetic correction. I'm just going to use the cold column kappa here, so that is in the cosmetic correction. So what does that mean? This is looking at outliers. This is a very effective algorithm, by the way, so be very careful the way you use it. I found, for example, that for this tutorial, 6 was a very good value. I wouldn't go lower, and I'm going to apply that now. So you can still see the image is at maximum stretch, and I'm going to reapply the calibration by just clicking on it again, and then this cosmetic correction will be applied to all our lights. And there you can see it has completely disappeared, which is very effective. This seems to be a good value for us. I'm just going to de-stretch the image a bit, 5 sigma, and I'm just going to zoom out again so we can just see the image a little bit better. You can stretch it as you wish. So let's go to the next steps of the workflow. First, I'm going to click on Analyse Stars. So what is the aim now? The aim is to get stacked or integrated images of all our single images. This final image for each filter will have a much better signal-to-noise ratio. In order to do that, we first have to analyze the stars. Then would be the next step, that is to register the stars. That means we have to match the stars on each image. Then we have to normalize the image, that's number 5. And that means taking into account the differences in atmospheric distortions or exposure times for each image that causes variations. And finally, in step number 6, we integrate the images for each filter. In the integration menu, we have different possibilities. As you can see, we can integrate per channel, and we can also integrate per channel and all. That's an interesting option, which is quite useful for fainter objects, because it means that we're adding up not only all channels, but we're adding these all into one super channel. So I'm going to leave it as it is, because we actually have a very bright object here. Now the good news is you do not have to go through all the single steps here. So again, we were at step number 2. We haven't done 3, 4, 5, and 6 yet. So you can start straight at number 6 and it will go automatically through step number 3, 4, and 5 for you. You can leave everything here at default and just click Integrate. Now this is going to take quite a while. Here it asks you again for the astronomical object name. We've already entered that in the beginning. By the way, if APP stops at any stage, there may be an error, and this is very common. It could be that your image is just not good enough and APP doesn't recognize it, cannot do the Analyse Stars or the registration, or sometimes the normalization correctly. Don't worry about it. Just scroll down to the image that you'll find in the lower window that is highlighted in orange, and then just deselect that single image. If you have further problems, or maybe you have too many images that are simply not recognized during a step, you can always go into that step and use the parameters there to refine the algorithm and wait until the integration process is completed. As you can see, the integration process has been completed. So let's have a look now what has happened and what image actually has been loaded here into our image viewer. So let's expand the lower window again. And as you can see, if you scroll right to the bottom of the lower window, there have been some new files that have been created. You can see here's the integration of the blue, green, luminance, and red. That's exactly what we expected. So that's the complete integration there. And as you can see here in gray, there's highlighted the red one. You can see the histogram on the right-hand side. So how good is the quality really, and what has happened here? Before we do that, let's just look here at the left window from the middle and expand that a little bit. This is the so-called FITS header, and that tells us a lot about the noise and many other things that are statistically important. Well, in total, we've integrated per filter over 14 images. So we would expect a noise reduction of the square root of the number of images, which is the square root of 14. So we can take a look here, and you can see that's the ideal noise reduction, the square root of 14, which is 3.74 here. We also have the realized to the ideal noise reduction, which is close to 1. It's larger than 1, so it actually shows that the noise reduction has been very effective. Let's close that again. So let's take a closer look here at the image viewer. This is our integrated image. And let's take a look at the quality first. I'm going to go to completely stretch it now to see if it has any artifacts. Let's stretch it a bit more. And you can see, I'm just going to zoom out a little bit. You can see that that is the red filter. And you can see that there's definitely here some vignetting that we have to correct later. But as we zoom in, we can actually see that the quality looks quite good. So what has happened to all our single light images? Let's take a closer look at them. Let's load the first blue one again. And you can see there is the linear image that we have up there. That is the raw image that we had initially before the bad pixel map and the cosmetic correction was applied. So let's go to the upper window and dynamically toggle to the next part. That's the step number 2, where the calibration came in with the cosmetic correction. Takes a while to load, but here it is. You can see the beautiful correction. And now let's step to the next one. That is the registration. That's the pattern recognition that aligns all the images. And you can see the image completely turned there to align it with the others. Let's go to the next step. Normalization, taking care of atmospheric effects and some differences between the images. And you can see the histogram on the right-hand side changed. So also that has been very effective indeed. And then finally, we have another tab called Star Map. So what is that? Let's click on it. And here you can see the stars that have been registered in the upper image. Here on the right-hand side, we find something very interesting. It's called the point spread function. And that is the median function over all stars. That tells you the differences. And it's actually, you can see it looks quite elliptical here. It's a Gaussian elliptical two-dimensional function that you can see here. And it shows that we actually have very little variation between the minimum of the full width half maximum and the maximum of the full width half maximum. So that shows that all in all, as a medium over all the different stars that we've looked at, the image looks quite well. Let's sort these all by quality. I'm just going to click here on the upper image, right click and say sort on quality, which I've done now. And then let's go to the image that has the worst quality. Okay, right to the lowest one. And let's double click on that and see how the stars look there. And you can see here, this is quite a strong ellipse. So you can see these stars are not round at all. If you zoom in, there you go. We zoom in and you can see that is more or less the shape that we are seeing here as a median. That is a medium over all the stars. Let's expand the lower window again and take a look what has actually happened. If we scroll to the right, you can see there are many statistical columns here. And you can see the complete analysis. For example, you can see something when the time was, the star density, the background dispersion, the signal to noise ratio, and what I told you already about the star shape and the quality score that has been given to all the individual images. There's some more here about the registration error and so on. You can see something about the instrument and the color space and so on. So I'm going to click the right click here on an image and just scroll all the way down to where it says create analytical graph. And now I want them all to be sorted by quality score. So let's do that. And you can see the result here. That's first. And we can scroll up to just convince ourselves. First come the blue, then the green, then the lumens and the red. And you can see from a normalized result of 1, the lumens have the best results. And here are the ones that didn't have such a good point spread function, but they will still be taken into account. And this is quite useful. You can play around with and experiment with very different settings here and see how different parameters behave. That completes this, and we can now move on to the next section.